In this video, we're going to look at Unit 1, Lesson 19, which is about evidence, angles, and proof, and we're going to make some convincing explanations. In this first activity, you should try to mentally evaluate all of the missing angles in each diagram. So the missing angles would be this one. You want to come up with this one. You also want to come up with this one. So you want to see in these diagrams, A and C, there are two different angles to try to come up with. In figure B, you have this angle, and this angle you want to come up with, and similar in figure D. So pause the video, go ahead and try and figure those out, and then come back to check your work. So in finding these angle measures, you hopefully remember that a straight line, and let me draw this straight line on here, but a straight line is equal to 180 degrees. So that gives us this angle down here. Whoopsies. That gives us this angle down here of 180 degrees. Then we know that these top two angles together total 180 degrees. So we could figure this missing piece out by doing 180 minus 50 and getting 130 degrees for that one. Then we'll apply similar thinking to these other ones. So I'm going to do figure C first. So the angle down here is 180 degrees. Then the angle up here, this one, is going to be 180 minus the 65 that's already used up here. That creates this straight line. And 180 minus 65 is 115 degrees. In this bottom photo for B, you see that there's two straight lines in here. So if we take a look at this, we see this bottom set of angles here and the 30. So this one and the 30 total up to that 180. So we'll do 180 minus 30 to get 150 for this one. Then if we take a look at this other straight line here, you'll see that that 30 goes along with this angle here as well. So this one here with the 30 also equals 180. So this one needs to be 150 as well. Then we could look at this straight line. So the 50 and this missing angle right here would give us 180. So this angle right here would be 180 minus 150, which would give us 30 degrees for that angle. So then figure D, this angle in here would be 180 minus the 135, which would give us 45 degrees. And then we'd similarly get 45 degrees over here. And then across from it, you'd have 135 again. All right, on this next screen, just think about some things that you notice and wonder about the diagram. You don't need to write it down. It's not in your workbooks, but think about what do you notice and what do you wonder in this diagram. So some things you might have noticed are these dotted lines. So you see kind of these dotted lines in each diagram. And maybe you wondered what they are. So what are those dotted lines? Maybe noticed that we've got a couple solid lines, and then the dotted lines are kind of always in between those solid lines. And then maybe you also noticed that these dotted lines look like, they almost look like a right angle in each case. So if we kind of highlight those, it almost looks like those make a 90-degree angle. So maybe you were wondering, is that a 90-degree angle in each diagram? And I'm sure there's other things you came up with, maybe the placement of that, of those dotted lines. Maybe you wondered if that's an angle bisector, is it in the middle, or how did they get that? what are those dotted lines? So let's take a look at that in activity 19.2. There's a figure that looks very similar to what we just said, and Diego's conjecture is that the angle formed by the angle bisectors, so those dotted lines are in fact angle bisectors. He is wondering, his conjecture is, if we do angle bisectors, will the dotted lines always form a right angle? So when we look at these dotted lines here, and I'm just going to highlight them here, but when we look at these dotted lines, the angle bisectors, is that always going to be a right angle? So he thinks it's always going to be a right angle. So label the diagram to rephrase what Diego is saying, and then determine if the conjecture is true. So pause the video and try a couple of things on your own to come up with how could you explain if his conjecture is true or false, and then come back to the video. So if you're having trouble labeling the diagram, we just want to think about what these dotted lines were, and remember that they're angle bisectors. And angle bisectors means that these two angles that the angle is getting split into are equal. So remember, we can put an arc mark with a little tick in there to say that those two angles are equal. And then that would also be happening in this other angle over here. This is the angle bisector as well. So you could put an arc and then with two ticks to say that those two are equal to each other. You could even go further and label it with some variable, because we don't know how big each of those angles are, but maybe you wanted to call them each X or A or B. And then this one, maybe you wanted to call something else to show that these two are equal to each other and these two are equal to each other, because we know that those are angle bisectors. So if you're having trouble with that, maybe do that and then label your diagram, and now see if you can come up with a conjecture, or if that helps you explain your reasoning here. All right, so let's take a look at doing this. So again, let's label this diagram. And so I'm going to relabel this on this screen. So we have these two angles that are equal. I called them both X. And then we also have these two angles, which are both equal, and I'm going to call them Y. And so rephrasing this conjecture is that Diego thinks that these angle bisectors of a straight line, okay, that these angle bisectors will equal 90 degrees, okay? And really in this diagram, what that's saying is that these two angles right here, right? So he's thinking here. So he's thinking these two angles, X plus Y in my case, if I want to put some algebra to it, that X plus Y is going to equal 90. So half of the one angle and half of the other angle are going to equal out to 90. So is this conjecture true, and explain your reasoning? Now there's lots of different ways you could have tackled this or thought about it. So one of the things is that it feels pretty intuitive if we start to think about it, that it would be 90, because this whole angle here is 180. So this whole thing is 180, and then we take half of it, right? Because we're taking half of this piece and half of this piece. So if we take half of it, those halves should equal 90, right? Because half of 180 equals 90. So maybe you tried to put that into words, just explaining it in words. If you wanted to put some algebra to it, so one of the things we could do is we could say, all right, well, we know all of these angles total 180, right? So we know that X plus Y, so those other two angles, so plus Y totals 180, right? All four angles. So then we can combine these like terms here. So we'd have 2x plus 2y equals 180. And when we do this, then we can kind of see, you see there's two of each of these. So I could factor a 2 out, and I could just say 2 times x plus y, because if I take a 2 out of 2x, I'm left with x. And if I take a 2 out of 2y, I'm left with y. So 2x plus y is equals 180, right? And so then you could just divide both sides by 2. And you're left with x plus y on this side, since 2 divided by 2 is 1. And then equals 180 divided by 2, which is 90. And this is saying half of the first angle plus half of the second angle equals 90. And that's what was in this diagram, because I labeled those x and y, right? Let me get a couple of these things out of here so we can look at that. But this is then what I have in here is x plus y. So this angle plus this angle totals 90. So that's what makes up those two dotted lines. So that's a convincing argument. One of the nice things about that argument is it doesn't use any numbers besides 180, which we know this totals 180. So then when you kind of split it up, that's the nice thing about algebra is it says if we have these two angles the same and we have these two angles the same, when we add them together, we know they total 180 no matter what those angle measures are, because they make a straight line. Then when we divided everything by 2, we end up with x plus y equals 90. Gives us a nice, concise argument that isn't specific to one set of angles. However, it would work in our sets of angles, right? So if we went back to this, and let me just clear this page out here. But if we went back to a couple of these, if I took and split, so remember that this one was 130. If I took and split this angle in half, this would be 25. And maybe I should make this bigger. That would probably be easier. So let me bring this down and make it bigger. So if I cut this in half with an angle bisector, then we know that each of these angles is 25 because that's half of 50. Remember that we figured out that this one was 130. So if I cut this angle in half, each of these pieces is going to be 65. And when I do 65 plus 25, that equals 90. And that's just one specific case to help you see that it truly does happen. It truly does give you a 90-degree angle. Obviously, that doesn't prove it in all cases. That was why we put the variables in with it. So if we did it again in this one, now we have a 65-degree angle. And so if we cut that one in half, that's going to give us 32.5 for each half of this angle. So 32.5, 32.5. And then if we cut this one in half, so remember that one was 180 minus 65. So this one started at 115. And if we do half of that, we get 57.5 for each of these angles. And then when we add these, 57.5 plus 32.5, we get 90. So that's giving us 90 for this angle right here. Let me do a different color. For this angle of those angle bisectors. All right. Then do you remember when we have angles that cross like this, or when we have lines that cross like that, what the angles are called? So we have these two lines that cross. The angles formed, okay, across from them. So meaning this angle here, and let me get a different color. But this angle here and this angle here are considered vertical angles. The ones that are across from each other. Also, this one is a vertical angle with this one. Okay, so the ones across from each other are called vertical angles. So that happens anytime that you have two lines that cross. You get two sets of vertical angles, and they're the ones, again, across from each other when the angles form. So let's take a look at activity 19.3, and what you're going to try and do is there's a relationship between vertical angles. And what is it? So you want to write down the conjecture. Remember, you saw some sets of vertical angles in this initial warm up here. And let me write some stuff back down on here. So we had this was 150, this was 30, this was 150. If you look back to this activity, we got this one was 135, we had this one at 45, and this one at 45. So when you're looking at vertical angles, so this one and this one are vertical, and this one and this one are vertical. Similarly here, we've got vertical angles here, and then vertical angles here. So what relationship do you notice between the vertical angles? That's what you want to talk about here, and then label the diagram to make it easier to write your conjecture precisely. And then how do you know your conjecture is true for all possible angles? And remember, when you do all, you don't want to do a specific case. Okay, so you don't want to just like put in a set of angles. You want to try and use some algebra or some letters. So go ahead and pause the video, try that, try a couple of things, and then come back to the video. All right, so there's some different ways you could have tackled this. Maybe you tried it with rigid motions. So maybe you talked about that there's probably some line here that you could reflect this angle over. And if we reflect this angle, it equals the other side. So maybe you tried that, and you know if that's true and I can reflect it, I know that a reflection is a rigid motion, so I know that it's going to stay the same size. So that's entirely possible. And let me just do that here. So if we reflected this, and then now my reflection doesn't work quite exactly on the computer screen, but I'll show you. Then you could get it, and you can see that those two angles are equal through a reflection. Okay, so maybe you talked about that and you were trying to figure out how to convince somebody that that actually does happen. Maybe you use some tracing paper or some different things. So let me put that angle back over. Maybe you talked about that it seems like you could rotate it, right? That you could rotate it around that center point and that it would land on the other angle. And maybe again, you tried that with tracing paper, you set your pencil here and you rotated the angle around and you saw that it landed on the other one. And maybe you did it for this top one as well. So you thought there was some way to make the argument through reflections and rotations. Okay, entirely possible. And then we'll get into how we can actually use those rigid motions a bit more precisely later. Right now, we kind of really only have the tracing paper to do that. So an algebra way we could think about this is if we take a look here, and let me get rid of this, is we could put some variables in here. So I could call this X, I could call this Y, I could call this Z, and I'm going to actually leave that one blank there. But if I wanted to prove that vertical angles were equal, that would mean that X is equal to Z. That's what I'm trying to prove. So remember, we know that this is a straight line. So we know the total of X and Y. We know if we take X plus Y, it equals 180 degrees, right? We also then know that we can similarly look at this line and see that Y plus Z is also equal to 180. Then through substitution, you know that both of these are equal to 180. So you know that they're equal to each other. You know this is equal to this. So we could set those equal to each other and say, all right, well, this one's equal to 180 and so is this one. So they are equal to each other. Then you could just subtract Y from both sides. And Y minus Y is 0. So we just have X on this side. And Y minus 0, or Y minus Y is 0. So we would just have Z on this side. And now we've proven that X equals Z. So therefore, your vertical angles have to be equal. You didn't use any numbers for the angles, just the fact that you know without a doubt that a straight line equals 180 degrees. And that then proves that vertical angles will always be equal to each other. All right, so then your lesson synthesis is which argument makes more sense to you? Did you like rigid transformations that take vertical angles onto another? So remember, that's where we had this line between them that goes through that intersection point, that line of reflection that would flip one onto the other. And you'd have it that way. You'd also have one that could go this way, right? And really, truly, it's the angle bisector. So it's the angle bisector of the other vertical angle. So we have that. Or talking about the rotation, right? So if we talk about rotating this angle around the center 180 degrees, so rotating it onto the other one, we could see. Or did you like using the angle sums, where we talked about giving these angles some variables? We know that both x plus y and y plus z equal 180. So they must be equal to each other. And then we subtracted y from both sides and got that x equals z. So which one did you feel better about? And then what is the difference between an angle and an angle measure? So an angle is actually talking about the angle itself, the picture of the angle. So looking at the picture or the diagram. When we talk about an angle measure, the angle measure is how big that angle is. And you would use a protractor to figure this out. So how big the angle is in degrees, and then remember that's measured using a protractor. So when we ask like, what angle are we talking about? We want to know the picture. And then when we're talking about what's the measure of the angle, then you want some number, like 20 degrees, 30 degrees, 40 degrees. So when we're talking picture, you're going to see things like angle ABC, angle X, okay, angle J, whatever. Might be using 3 letters, might be using just the vertex. When you're talking about how big it is, you're going to be seeing, numbers, 20 degrees, 17 degrees, 180 degrees, and so on. So go ahead and put this on your reference chart about vertical angles. So vertical angles are always congruent to each other, so we can see that here with the arc marks and those ticks. So this one is congruent to this one. So I'm going to put some color here. So this angle is congruent to this angle. And then this one is congruent to this one. You could even put some degrees in there if you wanted, or some variables. And remember that vertical angles happen anytime 2 lines intersect. So any 2 lines that intersect will give you vertical angles. Okay, 2 sets of them. So no matter how the lines intersect, the vertical angles are always going to be congruent to each other. Then your learning targets, hopefully now you can label and make conjectures from a diagram, and you can prove that vertical angles are congruent. Make sure that you do the check your understanding or the practice problems for lesson 19 in your student workbook. And if you need help with those, you can find the video that I have posted going over the solutions. And then you can complete your cool down. If you have questions on the cool down, make sure that you talk to your teacher to get some more explanation.